What is going on, guys? My name is Hussein, and ESNI is going away and they're being replaced with this beautiful thing that's called Encrypted Client Hello. So, what is ESNI? What is SNI to begin with? Server name indication. I talked about all that stuff right here. Check it out. I'm gonna also leave it in the pinned comment below because you guys said that you don't like me referencing stuff in the cards. You can't access them in certain devices. I'm gonna leave in the pinned comment below. But server name indication, if you don't know, guys, is the ability for a server to host in a single IP address many websites. For the longest time, if you want to host a website, well, you need an IP address, public IP address, then you need a domain that points to that public IP address. But if you want to host 1, 2, 3, 4, 5, 6, 7 websites, what do? Do you just spin up another IP address for each website and another domain name for each that points to this unique IP address? That's very expensive. You might know, right? Try it in Amazon. You spin up IP addresses. These things are expensive. So people came up with an idea called server name indication. So you can have your beautiful single public IP address. However, you can let the client indicate which server it wants to connect to by providing the domain name in the initial client hello in TLS. And I talked about TLS right here if you want to know more about it. So the problem with ESNI is it's unencrypted. So if people in the middle try to sniff your client hello, they can see what domains you're going. You're going to certain shady domains, they can see them, and you might not want that. So people from Cloudflare and Fastly and Apple came up with this ESNI, encrypted ESNI. I bet back in 2018 it became popular for a while, but it solved certain problems, but it didn't solve many, right? So people came up with a way, essentially encrypted SNI only encrypts that SNI, but guess what? There are many stuff in that hello that actually is plain text and kind of exposes the user privacy data. And we want to encrypt that stuff. So in a nutshell, encrypted client hello encrypts almost the entire client hello. But in order to do that, there is some work that needs to be done. I still have my criticism to this solution, despite it being beautiful and elegant. Let's jump into it. So most communication on modern internet is encrypted to ensure that its content is intelligible only to the endpoint, client and server. Encryption, however, requires a key, and so the endpoints must agree on the encryption key without revealing the key to be used to attacker. We fixed that a long time ago with Diffie-Hellman, right? An elliptic curve Diffie-Hellman. The most widely used cryptographic protocol for this task called key exchange and TLS Handshake. In this post, we'll dive into the encrypted client hello, a new extension for TLS that promises the significantly enhanced privacy of this critical internet protocol. Today, a number of privacy-sensitive parameters of TLS connection are negotiated in the clear. We don't want to do anything in the clear because invasive people in the middle, right? It might say, what do you mean by people in the middle, right? I mean ISPs, I mean boxes in the middle that content passes by, right? Or your stinking router, if you don't own it, like you're in a Starbucks, right? The client, the traffic goes through those routers. Are you okay with Starbucks knowing which websites are you going to? You might be okay with that. You might not be. So you have to worry about that when the time comes. So ECH encrypts the full handshake so that the metadata is kept secret. Crucially, this closes a long-standing privacy leak by protecting the server name indication. But we fixed this problem with encrypted SNI. Encrypted SNI has some limitation. I'm gonna save you the trouble, guys, reading this stuff. But encrypted SNI, essentially in a nutshell, solves the problem with SNI by encrypting only that encrypted SNI. But unfortunately, it has a lot of other limitations, such as it What if how do you encrypt it first? With what? You don't have anything to encrypt it with, right? And even if you do have something to encrypt it with, what if the server couldn't decrypt it? It turns out if the server couldn't decrypt your client ESNI, the client just disconnects and says, hey, F this shit. I'm not going to continue. And that's not probably, we need a way to, plus this is one way. The other way is just there is so much other stuff in the client hello that needs to be encrypted, like ALPN, application layer negotiation, the protocol negotiation. You're leaking the client and server capabilities, right? Client support HTTP 1, client support HTTP 2, the client server support HTTP 3. And if you know anything from security, you should, if this is information that the attacker shouldn't know, you shouldn't let them know. Just for the sake of hiding information. You need to encrypt as much as possible. Let the attacker have zero knowledge, because the attacker might know that, oh, client supports HTTP 1 and I found some hole in HTTP 1 that I can do HTTP smuggling, because HTTP smuggling is very hard in HTTP 2. It can be happening. I actually made a video where it did happen with HTTP 2. But with HTTP 1.1, it's very easy to happen, especially with proxies. If I know that you support HTTP 1.1, I can essentially take advantage of that as an attacker. So give as little information as possible. This is the background, essentially going through the ESNI, which we talked about. I'm not going to go through that. I'm going to jump all the way to the handshake. How do we do the handshake? The TLS 1.3 handshake. I talked about it many times on this channel. Let's go through this beautiful diagram. Cloudflare is the best company to explain it. Like, the amount of content they produce is just nuts. So this is the TLS handshake. The client sends a client hello. This is the original, not the encrypted one, right? It sends the extensions, key, share, SNI, ALPN. And this is a white box. And it says like a white box or what, no encryption. The extension, the key, the share, SNI, ALPN, all of a sudden they're clear. So if you're right here, you can pretty much sniff all of that stuff. That's what China does. That's what Russia does. That's what pretty much most ISP do, right? By looking at this beautiful value, SNI, server name indication. So they know what domain you go through. So they know what nasty domains you visit. As a result, they can block you from going there, or they can record the fact that you went there. Okay. And we want to hide that from ISPs. Because ISP, remember, if you want to visit something, you have to go through the ISP. There is no other solution. Right? The server takes the server hello. There is some non-sensitive extensions, like the key share itself. It responds with a server hello with one line, and then follows it back with an encrypted extension, sensitive extension. So the ALPN back from the server what actual protocol the server picked, what the certificate verify, right? The verification that the server actually owns the certificate, the server hello finished, all of the stuff is actually encrypted. You might say, how? Are we already ready to encrypt stuff here? Yeah, because that's the beauty of TLS 1.3. Immediately, the server can find out the pre-master key and pick up the algorithm and encrypt stuff and just shove it back, right? And then the client comes back and says, okay, I'm done. And then it will send the server the actual encrypted application traffic key. I didn't know that there are actually two keys here. That's a very interesting knowledge here. Then let's go through the diagrams to save you some trouble. So here's what Cloudflare did initially with Apple. It says, okay, we're gonna only encrypt the ESNI. So we're still leaking the ALPN. We're still leaking some other extensions. So attackers can know this stuff. So we're only encrypted this with the ESNI public key. So you might say, how did we get how do we encrypt this stuff? So in a nutshell, the client does a DNS and does a text query for the domain that it wants to connect to the server, because to connect to the server, you need to know where the IP address is, right? Where the server is. And you query the DNS with a text record. It says, okay, give me that is a public key that I need to use in order to encrypt my ESNI value, so sneaky people don't look at my ESNI value. And it says, okay, sure. You get that and you encrypt it, assuming the server has the corresponding private key that it will use to decrypt that stuff, because it's an asymmetric encryption at the end of the day. The servers take that, decrypt it, look at it, and then find out which domain name they want to go, and then pulls up the actual certificate that it needs, and then encrypts it with the application key that it builds from the key exchange that I talked about many times in this channel, and then just encrypts everything and goes back, and then that's what we do. What's the limitation of this? The limitation is that what if the server, remember this public key that we use to encrypt that, it's not really the public key of the server. It's not a static public key. Otherwise, it's not no longer perfectly forward. We need perfect forward secrecy in our stuff. So it's essentially ephemeral. Every hour or so, the DNS requests a new private public key, and the server has to generate a new private key matching that public key. So it always recycle, right? And what if you query as a client and you get a stale public IP address, and the server no longer have the corresponding private key that match that old stinking public key that you encrypt with? What if I can't encrypt it? If you can't encrypt it with ESNI, you're done. ESNI didn't say what to do. It was a very lacking protocol. It was very rushed. Let's put it this way. It was very rushed. Like, okay, what happened if you don't? If the server couldn't encrypt it? Like, okay, you can do whatever you want. No, just fail. That's what it does. It fails, which is bad. And here's what Encrypted Client Hello does. The Encrypted Client Hello has two parts, which is very, very interesting. And I'm going to talk about the limitation of this, in my opinion, right? First of all, it introduces a new Client Hello. There is a Client Hello outer, and there is a Client Hello inner. This is what you actually want encrypted, but this is what is in the clear. And you might say, what is the value of this ESNI and versus what is the value of this ESNI? So let's say I want to go to a server example.com, right? So you do a query, same thing, right? You do a query on the example.com DNS query, get the IP address, and you no longer query the text version. The DNS protocol has been improved to give you a beautiful record called the HTTPSSVC, I believe, that gives you the public key, the ephemeral public key that changes all the time of that server that you're going to use to encrypt not just the ESNI, just encrypt the goddamn entire thing, right? And in this case, you're going to encrypt only the client hello inner, because guess what? There is a chance that the server wouldn't be able to decrypt it, right? There's always this chance. So what did they do? Very genius. They included another client outer hello, DJ Khaled, another one. So the client hello says, okay, the outer one will include a value of ESNI that is pointing to a domain that is publicly known, and we're going to call this the client-facing server. And think of this as a reverse proxy. It's like, hey, this is your public server, right? So there is a hidden cost here, that now you want me to host two things instead of my just single server to support ECH, Encrypted Client Hello. You want me to host two certificates. My own certificate, obviously, and my own private key, with ESNI, and you want me also to host this other thing, right? Just this client-facing server that has to be public. Right? Let's take it in mind. So now let's go through an example, and I have to critique this article because they didn't draw a beautiful diagram with a failing example, but I'm gonna show you how it will look like. Don't worry about it. So the client will just send a client hello outer, client hello inner. This is the encrypted one. You might say, how did we get the public key to encrypt this part? Same exact thing that we did with the ESNI. It's just we're creating another account that is official, not just a normal text account. It's the HTTPSSVC. There's a whole RFC written for this decision. This is not something easy, obviously. So now the client takes that and encrypts the client hello, and that will have example.com in this case. I'm going to encrypt the client hello inner. But we can't send this just naked right there. We have to include another client hello outer, with the outer ESNI being the front-facing server domain. Let's call it server-ECH. Domain that we don't care if it was leaked, right? I don't care because it's not really, it is a real domain, but nobody actually goes there to visit. There's no content there. Okay, let's go through the example. So outer domain contains this, some outer extensions, the key, just a normal key exchange. These are two different key exchanges, right? The algorithm and all that stuff. So the server in this case receives this beautiful thing, this TLS 1.3 with all this extension that's called client hello inner. And says the first thing it does is it will not just respond to the client hello outer. No, it will try to decrypt the client hello inner with its corresponding ephemeral private key. And when it does, it will find out the inner ESNI, which is example.com. And once it does, it will know which certificate to serve and will just start building all that stuff. It will use the key share parameters in the client hello to build the key. It will take the key, take the algorithm, build the encrypted extensions, and then respond with the example.com certificate verification, approve that I own this certificate, and I'm finished. And then everything will be done, right? That's the happy path. That's the happy path. Well, the server wasn't able to decrypt this stuff, right? I don't know. The public key is bad. It was stale. The private key was leaked for some reason. And we want, and the server doesn't have that private key anymore. That public key matching is old, is bad. The server couldn't decrypt it. So in this case, where ESNI failed, ECH shine and says, okay, I'm gonna take your beautiful client outer hello. I'm not gonna fail. I'm gonna just I failed to decrypt this thing, so I don't know where you're going, but I'm gonna take the client hello outer and just try to establish a communication with you, sir. And guess what? You want to go to this ECH thing server that I happen to have this certificate for. This is another thing that I host, and it's okay if it's public. You want to go to this? Okay, let's finish up the encryption with that certificate. So the server will take that domain name, that ESNI, which isn't clear, and if it's okay if the server took that, if the attacker find out what that domain is, because we don't really care. And then we take that, we build the key exchange, we respond with what? We build our part of the key, the symmetric key, we encrypt the extension, and we respond back with the server hello. But before we complete that, before we reply with the server hello encryption extension, and we also encrypt something very, very critical. The public key that the client actually need to use, which is used an older one, right? The server will give this client the actual public key to use in order to encrypt the client key. It says, hey, by the way, you screwed up, client, use an old public key. Don't use that. Use this instead. And guess what? the attacker in the middle cannot see this because it's all encrypted with this outer client hello key exchange. So we're in the safe. We're good. I'm going to respond back. And then the server the client in this case, will take that, decrypt it, which is as almost nothing, right? It will be able to decrypt it because it's just another key exchange. But when it looks at the content, it says, oh, that's the public key. It will have information telling the client, by the way, guys, client, you screwed up. Your inner client hello was encrypted with a stale public key. Please use this beautiful public key. Right? And the client this is what the client will do. Will terminate the connection, kill it, close, send a fin back to the server, close that stinking TCP connection, and let's open a brand new one. Let's do a client hello outer with that same ECH server, the front facing server, and then the client hello inner in this case will be encrypted with the new public key that we just received. And we are very sure that the server this time is going to be able to decrypt it. Let's talk about the limitation of this. I'm going to reference this article, guys, right? One of the things that this is a problem. Protocol classification, which I talked about right here. The problem is that we're changing the semantics of TLS 1.3. We're introducing something new. And there are some boxes in the middle of the internet thrown around. They do not like new stuff. They just try to verify and validate every protocol by looking at the number of bytes, they're looking at the traffic, and TLS 1.2 should look like this. TLS should look like this. If you're introducing new things, I'm going to reject it. Unfortunately, that did happen with TLS 1.3. When we introduced TLS 1.3, middle router started to fail. So it's like, what the heck is this new thing that you're throwing at me? Kill it. So what the founders of TLS 1.3 did is like, they actually replaced the content of TLS 1.3 to make it look like TLS 1.2, which is kind of nuts if you think about it. Like the hacky things we do. Huh? just to make things work. Like, yeah, let's just make it look like a TLS 1.2 just so we can make it work. And Encrypted Client Hello is not going to be any different because it's a change, and we hate change. Not we, the middle boxes. So what the problem with this, guys? Obviously, there is no section in this article that says the problem because obviously they're not gonna. They worked on this protocol. They're not gonna say, "Hey, this is what's bad about it." They're gonna say only the good thing. Here's what's bad about it. We talked about the good thing, right? Now let's critique this protocol. First of all, the first critique, in my opinion, now we just increase the size of the client hello. So the packet size is bigger. In this case, we just introduced a concept of the possibility of segmentation when it's come to TCP protocol. Because we're going to start sending more packets. And the bandwidth is going to suffer, especially if you're establishing a lot of those TLS handshake. I'm not worried much about this compared to what's next. So here's another scenario where the public key that the client used to encrypt the client hello was stale. So the server is going to respond with another public key, right? And that should be okay. But what if that public key was bad? I don't know. There's a bug somewhere. Are we going to be in this infinite loop, right? Is this defined in the encrypted client hello, right? It's like, what will happen? How many times the client is gonna attempt to reconnect? Because I don't remember reading any protocol that there's an attempt to reconnect. We don't do that usually. This is a new thing to me. Right? I might be wrong, guys. Let me know in the comment section below. But the attempt to reconnect sounds dangerous. I mean, what if? Yeah, it seems like there is a possibility of an infinite loophole here. Another thing that I couldn't think of a solution to was like, what if I am hosting 100 websites, right, or 1,000 websites in the single public IP address, And how is it gonna work? Do I have a public IP, a public key cryptography for each domain? That mean in the DNS record there is example1.com with a public key, example2.com with a public key, example3.com with a public key, right? And then I have to figure out which one to encrypt it with. And if it is the case, like let's say the client actually encrypted with a certain public key and then sent it to me, to the server, how do I know which public key to which private key to use to decrypt the inner client hello? Like, do we just try all of them? Again, it's not clear in this article. Probably it's clear in the RFC. I'm pretty sure there must be an indication of, hey, by the way, I use this public key to encrypt your stuff, right? So in this case, the server can quickly check, right, which public key, which private key to use in order to encrypt. That's another thing I'm confused about. And the final one is just this thing that nobody talks about. Like you're asking me to host a new thing in my backend that I usually don't have to worry about, right? Like there is an additional backend management here. You have to host this new front-facing server with a valid certificate that you have to renew every time, and yeah, you have to do all this stuff, and then that's the cost of that might be insignificant to some people, but it is a lot of work. To some people, unless some web servers make this a little bit easier and behind the scenes, which I don't know how they're gonna do it, but it's very interesting. I think this loop has to be closed. I have still questions on when it comes to how this will be actually implemented. And as a backend engineer, what do I need to do in my web server to make this work? All right, guys, that's it for me today. This was Encrypted Client Hello. What do you think? Do you think this will replace all that stuff? And by the way, another thing I forgot to mention, China and Russia already blocked ESNI because they use ESNI to look to spy on their citizen to know what domain they visit, right? Because everything is encrypted right now. So with Encrypted Client Hello, do you think they can still block that? I think the answer is yes, right? Because it's clear that, hey, this stuff is encrypted, right? So I think it's going to be blocked. And if it's blocked, they cannot use Encrypted Client Hello to visit sites in China, right? Especially if you're a Chinese citizen, or you are in China and you want to visit some website, because this is definitely gonna be blocked for these big governments that needs to spy on their citizen. And guys, what do you think about this? This is a very interesting, elegant solution, I think, in my personal opinion. There's the back-end infrastructure pieces that I'm a little bit worried about, but I think it's not a really big deal. Let me know in the comment section below. I'm going to see you in the next one. You guys stay awesome. Goodbye.